Hi, I'm Naomi. I'm a mathematician, and one of the fields I study is inverse problems. So today I'd like to walk you through a very short introduction to inverse problems. So, first of all, what is an inverse problem? Oftentimes we'll talk about the forward problem and the inverse problem. The forward problem is the problem of calculating what should be observed from a particular model. An example of this would be we observe lightning and then we expect to hear some thunder. Now, the inverse problem tends to be a little bit more difficult to solve. The inverse problem is the problem of calculating a particular model from what is observed. So, for example, you observe a dog that's really happy, and you have to figure out what caused the dog to be happy. And that's a very difficult problem because dogs are always happy. So is it happy because its person just came home? Is it happy because it's in the sunlight? Or is it just a happy dog? So this can be a very difficult problem to solve. Now, mathematically, we are talking about a field of mathematics, and so it makes sense to put a couple of equations in here. We can write an inverse problem such as, on the left, we have y equals x squared. So the inverse of x squared is going to be the square root of x. And we can see that on the right-hand side. So on the right-hand side, we have y equals the square root of x, which is the inverse of y equals x squared. Now, a more complicated example is synthetic aperture radar, otherwise known as SAR. And this is a field that I have done most of my work in. So SAR is an example of an inverse problem. The main purpose of SAR is to create images of a scene from some moving platform, generally an aircraft or a satellite. So on the right-hand figure, you can see we've got this aircraft flying along some path. And what happens is it sends radio waves to some scene. It hits that scene and it bounces back. And so we collect those scattered waves. So we've got this antenna footprint, which this is a specific type of SAR called spotlight SAR because our antenna footprint looks like a spotlight. And so what we can do is we end up with this inverse problem. And if we're able to successfully solve this inverse problem, we end up creating an image of our scene. So it's pretty cool. So optical images are the images you are likely familiar with. So these would be pictures you take with a camera, with your phone. And this requires light. And with an optical image, we generally get a really nice image that looks like what we see with our eyes. However, there's a lot of hindrances. So if you imagine if you're in a dark room and you don't have a flash, well, you can't really take a picture. Or if there's a lot of fog and you want to take a picture from a plane down below, well, you can't see it. Turns out that SAR images can be taken regardless of clouds, darkness, rain, or fog because it doesn't rely on light. We're sending radio waves, and so we can use it in all of these circumstances. So here on the slide, we have some pictures, some SAR images, so you have an idea what they look like. On the left-hand grouping with the cars, we've got the far left is a SAR image of a vehicle, and then right next to it on the right is an optical image. And so you can see there are some differences between optical images and SAR images. And on the far right picture, we have a SAR image of the Capitol. And if you notice, the top portion of the Capitol building is maybe a little distorted from what you'd imagine, seeing from an optical image. So there are some differences. But remember, we can use this regardless of the weather, the time of day, so it's incredibly useful. That's a brief overview of inverse problems. Here's some references for the images that I used, and thanks for listening.